present RAPs 4, 5, and 7. Peter?
Thank you. Thank you, Brian. So my RAPs are 4, 5, and 7, and they have a lot of similarities, so I'm going to be combining some of the discussion so I'm not repeating myself in the presentation. The outline is very similar to the other RAPs. Is what's the purpose and when do we use these methods? Preparation discussion. Two of these methods use formwork, so I'm going to talk a little bit about formwork, material selection, placement curing, and checking for the quality. The RAP number 4 and RAP number 5 are similar but different. They both use formwork. So I'm going to have a lot of discussions that combine the two, and I'll show you the differences between these two techniques. The form and pump technique, again, uses formwork, and it's a little bit different. When do we use these methods? These RAP documents are really designed primarily around repair of spalled concrete due to corrosion of reinforcing steel. So anytime we have any vertical or overhead concrete that has this type of defect, these methods are appropriate. The surface preparation follows the ACI guideline, which is preparing around affected bars, removing concrete, clearing about 3/4 of an inch, squaring up the shoulders. One of the things that we highly recommend is that you don't do what was done in the past, which has been shown to create failure, which is just to knock the loose stuff off and apply repair material. I think this is true for all concrete repair techniques. This is not an acceptable method. I have taken, since I have 45 minutes, I'm going to try to drill into some of these references on preparation so that you can see the detail that we're recommending. This is an excerpt from the ACI video, which is based upon the guideline that was produced in 1989, and this is a shortened version of it without the sound. Oops. Certainly the first step, it doesn't matter if it's horizontal, vertical, or overhead, is to lay out the repair work. And it's very important to lay out simple configurations. Complex configurations like you see on the top there actually cause a lot of problems and generate a lot of extra cost. The preparation and removal process is either by hand removal with power pneumatic chipping hammers or hydro demolition. In general, vertical and overhead is limited to the hand methods, even though there are some applications where you can use the hydro. Structural safety is important, and safety of the structure really requires some attention to that aspect, and shoring is generally required. Concrete removal, as you can see here, is done with a 15-pound chipping hammer, removing the concrete down to the reinforcing steel, cleaning around the reinforcing steel, exposing the steel, at least so you can put your hand around it. That's the minimum requirement. And you chase it all the way to the where it enters into the concrete, making sure it's a well-bonded reinforcing steel to the concrete. You can see here where the hydro demolition was used, the bar was partially exposed, and that particular bar had no corrosion, which is it's acceptable to leave that bar without having any removal on the underside. You can see here the 15-pound chipping hammers removing the concrete underneath the reinforcing steel so that we get a good uniform environment with the new material. Vertical and overhead removals are very similar, as you can see here. The edges of repairs for all these techniques, all three of these techniques requires square shoulders, which is a combination of using cut-off saws like this, either hand or floor-mounted saws, making a saw cut generally less than half an inch so you don't cut the existing reinforcing steel. So a combination of saw cutting and hand chipping squares up the shoulders of these repairs so that we end up with a a uniform thickness throughout these repair techniques. And you can see here the saw cut was made, and we're cleaning it up with a 15-pound chipping hammer. We also, in these guidelines, recommend not to exceed 30 pounds in weight of the chipping hammer. This is a 15-pound hammer that was shown there. Many times contractors will use up to a 30-pound to pre-break down to the reinforcing steel. This is some examples of using hydro-demolition for the removal. Once all the removals are done, cleaning is required to remove the dust and debris and any bonding inhibiting materials. This is an abrasive blast that you're seeing here. And this is about 3,000 psi water pressure, which is the minimum required to do the same thing. Preferred method is abrasive blasting over hydro pressure, as you can see here. And this is a removal of the slurry from the hydro demolition process to make sure we get it down to clean, sound concrete. But this is typically, again, used for horizontal repairs. Any loose steel that's encountered in the repair needs to be retied. Many times when you're doing the demolition process and preparation process, some of the bars become loose. It's very important to retie those, as you can see here. Safety is obviously a very important issue with all these repairs, structural safety and also the protection of the workers. Locating and removing unsound concrete, as we saw earlier with the demolition equipment we saw. Clearing underneath the reinforcing bars. And then squaring up the edges, repairing any damaged bars. The edges, squaring them up, tying the bars, and then doing any final cleanup with the abrasive blast or water cleaning. That's basically what the ACI document 3730 talks about. One of the important things that we've learned, and is referenced in these documents, is the effect of improper surface preparation can actually cause a bruising. And if the bruising is not removed, number one, if you use the right equipment, you can minimize the bruising. But if bruising is occurring, it's very important to remove it, because this will become a bond breaker. Actually, a very weak bond will occur because of that. And this is just some examples of the microfractures that bruising will cause. The reinforcing steel, generally we're doing these repairs because there's corrosion. The corrosion products have to be removed. And the generally accepted practice is to use methods, whether they're abrasive blasting or, in this particular case, this small repair, we're using a wire wheel, is that we get it down so that we don't have anything that would inhibit the bond of the new material against the reinforcing steel. So that would meet the same requirements of new construction, which is any loose mill scale or any kind of corroded scale needs to be removed, and that's the minimum requirement. If there's a coating being applied, then the preparation system must meet the manufacturer's requirement. If the bars are damaged, it's very important that the bars be looked at by a structural engineer and a repair method determined, whether it's splicing or other techniques to repair the damaged reinforcing steel. The next step is in preparation to make sure that we have a structure, a surface that will accept the new repair material, and that's one of the purposes of the water cleaning and also the abrasive blasting, is to remove any of the materials that might be on the surface that would inhibit the bond and the absorption of the new material into the substrate. So we have a pore structure in the existing concrete, and that's what this graphic is showing, is that we have a surface that will absorb the new repair material. And that kind of leads us into the moisture conditioning. All these three techniques, the question is, what is the moisture content that's required? And we have really three conditions: the dry substrate, a wet substrate, which is saturated, and a saturated surface dry substrate, which is kind of in between. And if we go back to the issue of the pore structure of the concrete, if this pore structure is too saturated, has too much water in it, it will actually reduce the bond. So it's recommended that you really pay attention to this particular aspect of moisture conditioning. Sometimes we overdo it and actually reduce the bond strength by filling up the pores too much with water. We recommend that a mock-up be performed with all three of these techniques to demonstrate the preparation, the moisture conditioning, whether a bonding agent is used or not used, and then the placement technique. And then these results can be evaluated and modifications to the procedures can be determined from there. The material selection process, for the form repairs, obviously you need something. We have a great flexibility of what materials go in there based upon the fact that all that's required from a construction standpoint is that they can be placed into a form and consolidated either by the nature of the material itself or through some type of vibration. And in thin repairs, there's a lot of prepackaged materials available on the market, and these may or may not be polymer modified. Some of these may have the self-consolidating admixture. On thicker repairs, ready-mix concrete is generally a very standard material with a minimum of half-inch aggregate. 3/4 or larger is recommended to reduce the shrinkage. These repairs will use admixtures including high-range water reducers and SCC or self-consolidating admixtures to improve the flowability. The other aspect of material selection is the shrinkage issue. This is work that Paul Carter did in Alberta doing uniform tests on 46 different materials. And each of these repair materials, you can see the variation in shrinkage. And through other work done over the last 15 years, we've determined that drying shrinkage of repair materials is a critical property. And the less shrinkage generally is a correlation between the less shrinkage, the less cracking that will take place. So it's believed that shrinkage below 0.05% in accordance with C157 is the recommended material. So you can see that many materials do not meet this requirement, and it's a critical aspect. Just in relation to this particular chart, ready-mix concrete is about 0.05%. So, and that's really due to the fact that you have a well-graded aggregate, larger aggregate, than a lot of the prepackaged materials that are represented in these 46 materials, which are generally more fine aggregate, more cement content. These are the effects of the shrinkage. You can see the shrinkage cracks. This is a horizontal repair, and these are some vertical repairs. They basically manifest in these cracks that really bring into question the viability of the repair work. So we want to avoid these by selecting the materials with low shrinkage. Finding these materials either through a mix design using ready mix, or in this particular case, if you're using prepackaged materials, the material data sheets that are available from the manufacturers generally provide information about these properties, and selection can occur by finding these properties. And in some cases, the data sheets actually don't have these properties listed. So it's very important, if these properties are not listed, to talk to the manufacturer and get that information before you make a purchasing decision. The other thing that's very important on work that's done with formwork is, especially on the overhead form repairs where we're pumping or placing material from the top, is the bleed water issue. So the mix design must have a mix design that does not allow any bleed water to come up to the surface. Otherwise, that bleed water will accumulate at the interface, right in this interface between the new and the old, actually creating a bond breaker. So if we look at the form and pour technique, which is basically building formwork and placing material behind it and then consolidating it. If we look at these procedures, these are some of the graphics that are in the RAP document. And it's basically constructing formwork, placing the formwork up using some type of anchoring system. Again, this can be vertical or overhead. In this particular one, we're working on a wall. We're placing the material behind it, then we're going to vibrate it, and then we're going to strip it and make sure there's proper curing. This is the same technique for some overhead repairs. Actually, we've cut some holes from the top. We built some formwork, and the material flows down through these holes and fills up this cavity. This is a very easy way to do an overhead repair. Again, this is a schematic of that. You can see the prepared area. This is the material, and this is what the formwork. These are some examples of applying this method to some existing structures. This is a clarifier where the top of the concrete on this outside wall is deteriorated from its exposure. Concrete's been prepared. In this particular case, we're using two-sided formwork, very similar to what you would have in new construction. And ready-mix concrete's placed in there, and this is what it looks like after it's stripped. This is one-sided forms. Where in this particular job, this is a sulfur trench where rail cars of molten sulfur dump molten sulfur in this trench, and then it moves down this trench into another area. The molten sulfur has attacked the concrete, and it requires repair. So the method of repair here is to build a trench within the trench. And you can see the formwork. This is one-sided formwork, and there's a gap here between the formwork and the existing concrete. And this is what it looks like. So basically, it's just using a special, in this particular case, a silica fume concrete was used for its density and resistance to the same deterioration mechanism that the original concrete went through from the exposure of the molten sulfur. This is another example of smaller repair on a wall, and you can see the formwork. It's one-sided formwork. These are the chutes that the material is bucketed into, and then the formwork and the concrete is vibrated. Now, the liquid pressure head is a very important consideration. Even though this repair is only 4 inches in depth, the same liquid head develops. No matter, it's based. The head is, and the pressure on the form is based on the vertical height. It's not on the thickness. And you have to design the number of anchors based upon the loads that are placed on it. And there's some guidelines from ACI on the formwork that can be used. So you can see the materials being placed in buckets down these chutes. There's different configurations. Here's another use of some, these are the column forms. These are cardboard forms that are used for new construction. They've been split in half and then recombined around this column with a chute on the side, and this is the finished job. So very straightforward repair using conventional materials and somewhat conventional modified formwork. This was actually a repair installing some new beams in an existing structure. This is the site of the Detroit ACI convention a few years ago, and the tower that we all stayed in. And this was some new wind bracing that was added to stiffen the building. And in this particular job, using this form and pour technique, we use conventional form panels. So it's not always custom-made forms. In this particular case, it was just off-the-shelf form panels. Consolidation is extremely important as in any construction. There's no difference here. This is a schematic showing the insertion of a pencil vibrator. And this is an actual job where you can see the bottom of this beam is being repaired with the formwork surrounding the bottoms and the sides. And you can see the chute here and the pencil vibrator is inserted in the chute to consolidate the material. One note on the construction of the formwork. When we have one-sided forms, it's very important to have an anchoring system that will support the loads. And this particular, a very standard method is using coil rod, very conventional to formwork construction. In this particular case, use rock anchors. And the rock anchors basically carry the load into the existing structure and out to the formwork and into the supporting whalers. And some of the things that we've learned about this technique is it's very important to preload these anchors. Some anchors, like these conventional coil rod anchors, need to be pre-stressed so there's no slippage when you load them up with concrete. Otherwise, the formwork will actually slide and move and bulge. This is an example of some formwork. You can see the heavy nature of it. This is some very heavy repairs using this technique. This is a short video clip showing this is from a manufacturer's training video using some material that's designed for this type of technique, the form and pour technique. And he's quickly going through some of the preparation techniques, the abrasive cleaning, some saw cutting, some concrete removal. Some of the safety procedures, the personal protective equipment on some of these videos is not up to the current OSHA standards, as you can see. Some eye protection and hard hat protection is not really the current standard. This is the formwork that's being used to support the new material. In this particular case, they're pre-wetting the concrete by filling up the form with some water and then draining it. Again, it's very important not to have too much water in there, otherwise you're going to have a bond breaker. This particular material has been designed specifically for this. It's very similar to self-consolidating concrete, it's very self-flowing and self-leveling. Actually doesn't require any vibration because of this material design. Personal protective equipment that would be required here would be respirator for dust, possibly ear protection, hard hat, and eye protection. This particular material is obviously prepackaged and mixed on site, bucketed to the location. You can see the flowability of this material. We've come a long way over the last 100 years, and these materials that have this kind of flow characteristics have really enhanced the ability to do these repairs, even with very dense reinforcing steel. The flowability without vibration really proves that these materials are really suitable for this type of repair. Okay, so that was the just quick discussion of the procedure on the form and pour. I'd like to talk about the form and pump technique. Now, the form and pump technique is different in the fact that when we're pumping using the form and pump technique, we actually pressurize the form using a pump, a hydraulic or some type of pump that pumps the concrete or the mortar into the formwork. We actually pressurize the form, and that pressurization is what consolidates the material around the reinforcing steel and drives it into the pore structure of the existing concrete, resulting in a good bond. So that's what this technique is. So it's very similar, same kind of preparation technique. We're building formwork that will resist the pressure and will have some kind of connection to the pump line, which I'll show you in some slides in a moment. The use of different materials that are used for this technique is basically anything that you can pump can be used. So it's not limited to fine aggregate. We've pumped jobs with 3/4 inch aggregate into these kinds of jobs. The formwork needs to be designed for the pressures, and generally what we have found is the minimum requirement is 15 psi, which doesn't sound like a lot of pressure, but it is a very stout form. That's about 2,250 pounds per square foot of load, as it has to resist the pressure of the pump line, and especially at the point when you cap it off. These are some examples of, this is a bottom of a beam, and this is a reinforcing steel, and this is plexiglass formwork, so you can actually see the material flowing through the bottom of this beam. We're filling up the bottom of this beam with this particular technique, and the series of pictures, the first picture is one I'm showing here, is the pump line is connected to the left side, and the material is moving into this form, and you can see the leading edge right here in this particular location. And the next slide is moved from there all the way over here, and you can see how it's kind of building up a back pressure as it's moving from this location to the other end of the beam. And as it builds up the back pressure, it starts to push it up against the existing substrate, encapsulating the reinforcing steel. And this is the last in the sequence, showing that the cavity has been filled, the form is pressurized, and there's actually some pressure gauges you can see right here, and we actually pressurize it to about 14 psi, at which point the valves are turned off, and you can see how this consolidates it by just the pressure of the internal pressure, how it pushes it around and consolidates, and especially the intimate contact it develops on the upper side with existing concrete is. The way these formworks are attached to the existing substrate is either through a tensile anchor like this, or through a compression anchor using, in this particular case, overhead repairs, simply using some shore posts. So the shore posts are screw tight so that these forms that are basically, there's very small repairs beneath these forms, and the pressure that develops is reacted against these shore posts. These are just showing some different attachments and different locations. So these are the port locations, and these are actually some very low-tech valving made from the hole saw that cuts the holes. They're nailed to these pieces of plywood, and as the hoses are removed, these are slid over and to seal those locations. In some bigger jobs, we've actually, this is an overhead repair using this technique, and this formwork is actually dropped down in this location. It's actually going to be raised up against these cones right here. And these pieces of PVC pipe, they're cut on 45 degrees, are actually air vents at some high spots in this particular job. This is very heavily reinforced. There's actually a turbine pedestal with a lot of reinforcement, which is an excellent location, excellent application where you have a lot of reinforcing steel to use this technique. This is an example of a job where this technique was used. This is a arch bridge. You can see the concrete that's been removed. These are the form panels that are being installed. They're anchored with tensile rock anchors. And concrete is then pumped from ready-mix trucks. We're using a conventional hydraulic pump. And actually on smaller jobs, you can use a pump like this, which is actually a small slab jacking pump. It's a piston pump. It's not a Moyle pump that Doc was referring to. This is actually a piston pump. You can actually put a 3/8" aggregate in it, and it's good for small jobs. So going back to this arch job, where we use the big pump and ready-mix concrete, we're going to start pumping at the bottom, and we're going to pump it up. And that's basically very similar to all the techniques that we're hearing about today, whether it's epoxy injection, pre-place aggregate, or in this particular case, the form and pump technique. Concrete is pumped at the bottom, and it's allowed to flow upwards. And in this particular case, we had ports every 10 feet where we pumped until it came out the next port, and then we moved the pump line to that next location. And we went all the way to the top. And then we did the same thing on the other side of this arch until we came to the top, and then we finished. And then we stripped the forms, and it was a good job. Now this is an example of another application using this technique. This is an offshore platform out in the Gulf of Mexico, and this particular structure was subjected to the salt exposure of the seawater, and over many years deteriorated. So the concrete's been prepared. Formwork's installed, and we use the same technique where we're actually site mixing, or basically a ready-mix concrete on barges, pumping it into these forms. This is an example of the new and the old connection. And I show this picture. Sometimes everything doesn't go right, and the importance of quality control, even these are kind of high-tech procedures that if you don't fill up the formwork, you're going to have the repair of the repair. This is what happened when you stripped the form and you had some cavities up here because the formwork wasn't fully pressurized. So that's part of the quality control procedure, is to make sure in a technique like this that you're actually filling the formwork and loading the forms. The last technique, which the first two I talked about were form techniques, the form and pour technique and the form and pump technique. The difference between, just revisiting that, the form and pour was basically gravity feed behind formwork, and the only pressure head was the liquid head of the material, versus the form and pump technique, which is you're actually adding pressure from the pump line. So you have the existing head from the material plus the pump line pressure up to 14 psi. So we'll shift gears and we'll talk about RAP number 7, which is the most conventional repair, which is horizontal repairs, which you would find on bridge decks, parking decks, and other horizontal surfaces that are subjected to some type of deterioration mechanism. One of the things that I mentioned in the ICRI preparation video is the layout. Layout seems to be a bigger issue on horizontal repairs, and you may have a surface that has different types of spots all over it, and if you sounded it, you might have a little bit bigger area. If you were to do a strict layout based upon the delaminations, you may end up with something like this. The guideline highly recommends that you use and make this a much more uniform layout. which generally is a big conflict out on a lot of jobs. Some of the owners don't want to spend, they think they can save money by cutting out the square footage around these areas, but what ultimately ends up is a very poor repair that's going to go through a lot more repair and potential reentrant cracking and other things. So this is the recommendation of this guide. Full depth repairs are special. Anytime we're doing horizontal repairs, the selection of the material is really critical for low shrinkage because we have no restraint for any type of movement that takes place. But we do have the boundary of those repairs that forms a fixed point. So any shrinkage that takes place will manifest itself generally in some type of cracking. So the selection of the material for reduced shrinkage is very important for full depth repairs. The same thing is true on edge repairs of balconies when we're doing full depth repairs. Balcony repairs are a big work item along the coast, East Coast, and shrinkage cracking will occur there also. This next sequence I'm going to show you is basically standard process, whether it's partial depth or full depth. And in this particular case, we're using ready mix concrete. Obviously, the placement into the location is the first step after all the preparation is done. You can see the next step after placement is the insertion of vibrators. And this is probably the step that's left out the most in these particular jobs is the lack of vibration. And it's extremely important to vibrate as in any job, even if it's 3 or 4 inches thick, to consolidate around the reinforcing steel and also to create intimate contact with the substrate. Now this next video just shows the importance of that. This is a glass form on some low slump concrete. A vibrator has been inserted, and you can see how the vibrator liquefies the concrete. And we show this in training just so people can visualize this and appreciate this so they don't skip this step. Even if the repair is 3 or 4 inches thick, it's extremely important to get a good bond and encapsulate the reinforcing steel. The next step, and I've got some steps in here that may not be required, but in hot weather, after the initial screeding, an evaporation retardant is placed on this material, only because sometimes in thin repairs, horizontal repairs, you have, if it's hot and windy, you could have rapid evaporation and plastic shrinkage cracking can take place. So immediately, this product, I guess, was developed sometime over the last 10 years or so. It's a great product for this type of application where you have thin repairs that are susceptible to plastic shrinkage cracking. Then the next step is floating. Again, we're following exactly the same procedures as new construction. We're going to float the surface, followed by, in this particular case, Fresno, which does a little bit more leveling, knocks the bumps out. Again, this step can be eliminated in a lot of applications. And then some texturing. Again, texturing is not always required. In this particular job, the broom finish. And then there's a curing process. And curing can be either a membrane curing or a traditional wet curing. In this particular case, they're using burlap, which is it's important to keep it there, obviously, for the specified duration, 3 to 7 days, depending on the specification, and follow in this particular case with some polyethylene to protect that. The mix designs that are recommended here are, in traditional ready-mix applications, a minimum of half-inch aggregate. One of the industry trends is to go with pea gravel. That induces more shrinkage. The real recommendation is to use 3/4 inch or higher. You know, if you can get 1 inch or 1.5 inches for some of these thick repairs, you're going to cut down the amount of shrinkage. A water cement ratio less than 0.4, not 4, sorry. But a lot of horizontal repairs, prepackaged materials are applicable. I'm just going to show you one example. This is MagFaz rapid setting material for some runway repairs. And you can see the preparation's already been done. This is some spalling, edge spalling along some cracking in the runway slab. And there's a lot of good materials out there that are especially designed for this rapid setting, so we have low shutdown times. You can see in this particular repair, a key item was the forming up the joints so that we didn't have reflective cracking through the repairs. So the video probably sped up the process a little bit, but you can do these repairs within a couple hours, which is nice. So selecting those materials, there's lots of those materials available. So let's talk about quality control systems for all three of these methods. Obviously, we're looking for the quality control of the material itself. And basically, we're going to follow, the recommendation is to follow all the same things we do for new construction, whether it's slump, air, cylinders for compressive strengths. These are all basic standard formats, and it's for prepackaged materials and also for the ready-mix type materials. The other aspect that makes repairs special and different from new construction is you're making a new type of material. You take a repair material and an existing material, you're making them as one. So you want to check the quality control of the in-place system, which is a bond test. Now I've got a couple of slides here in sequence. Okay, well that's interesting. Okay, well, as Doc said, it doesn't always go as planned. You core drill down through. The basic procedure is outlined and some guidelines I'll mention to you in a second. Core down through the repairs into the substrate, and you glue a dolly on, and then you put a device on it that pulls on it very quickly, and you interpret the results. So there's actually two new guidelines for that are referenced in this RAP document. The ICI one is 3739 that just came out last year. It's probably the most complete, and it's designed specifically for the repair industry. It's not a modification of one of these tests used for something else. So the 3739 is probably the best one, and it goes through the procedures, it goes through the recommended values, and then ASTM has recently come out with one also that goes through an ASTM test method. So this is probably the most important quality control that we can put onto these jobs. And these are some additional references that are available and referenced in the RAP document. So that brings us to a conclusion, all three RAP documents, and I guess we'll take some questions if there are any. Yes, sir.
Are you using any fibers, plastic fibers in your concrete for shrinkage control?
So the question is, are we using fibers for shrinkage control? Generally, we do, so on occasion, use fibers, but for plastic shrinkage, generally plastic shrinkage is not a big issue if you follow these other procedures. We don't normally have that, but if you were going to anticipate that and didn't want to do the other things, I'm sure you could use some plastic fibers to minimize that.
Can you just go over the guideline for exposing rebar? I'm thinking about a lot of flat work where you may have just rebar on the top surface, and if you've got to expose both layers of rebar, the mat will just come through, come free of the concrete surface.
Okay.
So
So in a typical elevated slab, you have a top mat and a bottom mat, and each mat has bar in the X and Y direction. So you're talking about when you expose that top mat of the two bars in the X and Y direction, it's kind of floating there. Is that your question?
Yes, right. And also, I'm thinking about slabs on grade, maybe if you're doing repairs there, where you've only got one layer of rebar maybe in the top.
Okay, so if you're doing isolated repairs, the boundary holds that reinforcing steel in its proper location, so it's generally not a problem. If you're doing a massive repair, like in using hydro demolition, you may have the mat, fully there flopping, and you're going to have to stabilize it prior to placement. So, does that answer your question?
Well, what about the exposure? You were saying that if you've got corroded rebar, you want to completely expose that and then go get a hand underneath it.
Yes.
What is the guidelines if you don't have, badly corroded rebar, and the engineer's looked at it and says, that rebar is still acceptable?
Okay, so the question is, if you uncover a bar, there's a couple things the guidelines speaks to, and all these things can happen on every job. If you have a delamination, you're digging down and you uncover a corroded reinforcing bar, the guidelines are very clear. If the bar has any corrosion whatsoever on it, you've got to uncover it and expose it all the way around, put your hand around it type of thing. The other thing the guide says, and through the excavation process, you may be the top X bar versus the Y bar, there's 90 degrees to it, right underneath of it, may get exposed as part of the undercutting process. So the top bar is partially corroded, so you're required to undercut that. And through that process, you may uncover the next bar, but if it doesn't have corrosion on it, you don't have to expose it unless you go more than 50% around the circumference. If you start going more than 180 degrees around it, then you've got to uncover it, even if it doesn't have corrosion.
Which I guess would be most of the cases, wouldn't it? Because if you've got, unless it's a really big bar, if the smaller bars, to get a hand in, you've already exposed a good portion of that bar underneath.
Yes, and
In that case, you need to go all the way under that one as well.
that's in theory, but it might be just a spot underneath where the intersections are, and it's really an engineering judgment. You don't have to take the guideline literally, but that's, you just have to look at it from a practical sense. Some people take it literally, and there's a lot of unnecessary work done to do that. The important thing is that you're creating a uniform environment around the bars that have an environment that caused the corrosion, whether it's chlorides or carbonation, so that you're creating a uniform environment. Now, just because it's not delaminated or showing corrosion, you still may have a lot of chloride in the concrete. That's why you want to remove that. And of course, if you really want to get into some really detailed work, you do some of the carbonation testing and some of the chloride testing, and if you still had that, you could be excavating more of that concrete so that you wouldn't have more repairs 5 to 10 years down the road. Yes, Paul?
Pete, what you just said partly addresses what I was going to ask, but not totally. I was just wondering, on RAP 7, which is spall repairs, I just wondered, you made a brief mention about using corrosion inhibitors in the patch, and I just wondered if you had any suggested guidance as far as preventing the halo effect in areas where you have a uniformly exposed surface to chlorides, and you're only patching certain parts, I think.
All right, so Paul is asking the question is if we have a repair, and if we're changing the chemical environment of that new material, whatever we put in there is going to be a different chemistry than the surrounding, and we have the option of putting some more admixtures in that material, like an inhibitor, and what is the guidance on the halo effect, which is, are we going to accelerate the corrosion around it? And I think in theory, it says it will, right? I think the corrosion theory says it will. In practice, we go out there and we see, after 5, 10, 15 years, our repairs, and it can be some more corrosion taking place around it. Was that caused by the halo effect? Or was that just ready to go and it just hadn't gotten there yet because the chloride was still there, it just hadn't gotten down to the bars? I don't know the answer to that question. We do know that what we have learned is that if we take an approach to do spotty repairs on a structure and it's kind of spotty all over the place, it's going to have lots of repairs later in between those repairs. And most sophisticated owners now take the approach to do more global removal and just deal with it at once instead of doing the spotty repair, and you end up with kind of a job that ultimately is going to have a lot more cost expended. Is that pretty much what you feel, Paul? Okay. Yes, sir.
Yeah, if you're doing repairs to the top steel of an elevated concrete slab, would you take the deflection out of that bay before you made the repairs? Or just make the repairs without propping up from below.
That's a good question. The question is if we're doing repairs out in the middle of a bay on a slab, like the top surface, and obviously we're changing the load path. We're taking out, in the top of that slab in the middle is theoretically in compression, and we're taking out the compression concrete. If we didn't shore it up, it's going to probably deflect. Almost certainly deflect, because you're taking out some of that compression section. So I think in most cases, there's a shoring plan, and most plans that are out there don't jack it up. They just stabilize it where it is before the removal process. I think in theory, you're absolutely right. The ideal thing would be to jack it up and put the new material in there and then take it down so it's preloaded, pre-stressed when you're in service.
You're not engaging in steel.
Yeah, you're not engaging it. So I can't tell you, probably on 2 fingers, in 30 years I've seen a specification call for that, even though the theory says you should do it. So practice is that you don't do that. You put shoring in there, and I think with all the repairs that are done that way, there's not been any failures. It may not be a perfect engineered solution, so I don't know if the cost would be justified based upon the practice that's out there that seems to be working. Anybody else have any experience on that? Okay. All right. I guess that's it. And one more?
Could you just talk about the relationship between this committee and the international contractors repair?
ICRI?
Yeah.
What's the connection between RAP, the RAP group, and the the ICRI group?
Obviously, they're separate, organizations, but is there any guiding principles in terms of what ACI is trying to do to supplement or complement what?
This is a yeah. Yeah. There's a lot of work done around the world on all these topics, and there's a lot of overlap. And here in the United States, I guess the 2 main groups that work on repair stuff is ACI and its repair committees, and other committees that work on repair stuff, which I think, Jim, there's 20 or 30 committees working on repair stuff in ACI. ICRI was started about 1988, so it's about almost 17 years old. And it has focused on similar projects, but more practical projects. I'm not saying that the ACI documents aren't practical. The RAP documents are as practical as you get. So the way projects are developed by each group, there's a big overlap in the membership. People here are also members of ICRI, so those members try to make sure we're not duplicating things. In tradition, the RAP documents are the kind of documents that ICRI normally produces, that kind of style documents, they're practical documents, and ACI is more engineering-oriented type documents. So how this thing evolved, it was just the idea of some people in ACI 546. The repair committee came up with this, and it started, getting some traction, and these documents were created. And then the Educational Activities Committee decided it belonged to them, and it wasn't a TAC document, and so EAC, they weren't technical enough for our TAC to get excited about them, so they became an EAC. They're educational. That means that all other documents are non-educational. So I don't know if I'm just rambling a little bit. I think in practice, it would be nice to have everything organized as one thing, but we have 2 organizations working on similar things, both accomplishing a lot, but there is some overlap. Bob?
Just one other comment is that you'll find that people at ICRI have a very strong contracts with them, and that's where the practicality speaks to. You read those documents, and if you were a contractor, you get something out of those documents, very, very much so. ACI is opposed to allowing contractors, more designers and material commissions, whereas ICRI is just the other way around.
Yeah, I think the practicalness of these things is really the importance, that we're trying to do more practical things. Randy?
Peter, I've got 4 more minutes before our break, as it says in the book. So I was wondering if you could discuss briefly or get the group, since there's so many people in here, to talk about where this committee is going for the future in relation to the repairs and the procedures. We have a good assortment of information as it's been presented. Where is it going towards environmental concerns like protecting the environment from dust, water contamination, things like that? I thought maybe you could get a discussion.
Well, these documents were never designed to be a complete treatise of the topic. You know, from a contractor, how to set up the dust barriers, the environmental things you're talking about, or the safety things. So these are very short informational documents to help give a person a concept that these are available. This group, and I don't want to speak for the chairman, but it's okay?
Go ahead.
Our mission is basically to produce as many of these short style documents, and I've actually, in my discussion, covered a lot more material. I covered a lot of stuff in the references. So the basic document is going to be pretty much like you saw in the earlier presentations, covering a lot more topics. So I think we are up to, what, 20 of them, Dave?
I think we're at 23.
23? So
This is the first 10.
yeah, it took us, what, 8 years to get this? And I think, but we're on a roll to produce them more efficiently.
Peter, and there was a question about environmental issues. Throughout the United States, and probably in other parts of the world as well, there's an awful lot of secondary containments for the chemical and maybe chemical industry, I guess, where they were designed in an old style. You basically had an octagon or a circular foundation below the tank.
Mm-hmm.
They put up a ring wall with a spread footing, and then they poured a slab in between it. And I don't know how they could ever classify it as a second contained structure, but that's how the majority were built many years ago. There's an awful lot of those around today where it's not that practical to go in and just tear those apart, temporarily relocate the tanks and rebuild it, or have enough space to rebuild it somewhere else and then move the tanks over one by one. Is there anything in either of these two organizations where they've addressed that issue of trying to repair those types of facilities?
That specific type of technique for that specific structure?
Yeah.
Not that I'm aware of. I mean, you'll find parts of different documents that can tell you some ways to do it, but I don't think there's a procedure that's been developed for that. Anybody else aware of anything? Okay. So is that a wrap?